Um, okay. Some other minor things again, we'll come back to all of these and dig into details. Um, Package manager is awesome. Project management in terms of like linking in READMEs, specifying what your dependencies are, sort of all the stuff that's become common in like npm block files, PyProject TOML. Um, as code languages have matured, we've kind of moved into project metadata being part of the code base. And Rust is a recent enough language that they like, hey, that's a great idea. Let's do that from the ground up. And they've done a great job with it. Test-driven development. People talk about this. There are lots and lots of talks online about how awesome test-driven development is. In Rust, it's almost harder not to do this than it is to do this. And I have found that Rust not only makes it so super easy, it encourages me to do this. It makes it very straightforward, just sort of to build up test-driven development, build up my code using test-driven development methods. It's incredibly performant, and it has just been a massive boost to my productivity. And even having learned those lessons, I still don't do test-driven development on Python because it's just so much harder in Python than it is in Rust. So come back to that. Mature communities. Rust is obviously nowhere near as big as C, C++, Python, Java, JavaScript. But it's a pretty close second past beyond all those. You've got a community that's really trying to make Rust a competitive language on higher level applications. So web backends, even web frontends, competing with React. I'll talk about that. Building Python libraries, CLIs, textual UIs, game engines. There's frameworks for everything. And so it's even though it's not a very old language, it's about a decade old at this point. There's a lot of maturity around building real world applications that are incredibly performant. Macros are amazing. We won't dig too deep into that, but we'll come back to that bit. And data processing, actually. I use Rust for a lot of data processing operations. And there's some really cool stuff about how a lot of language features in Rust come together to make sort of iterable, lazy, iteration and data processing kind of an amazing thing in Rust. So what's not to like? Let's get to that. All right, before that, the history of Rust. Where did Rust come from? So it was invented in 2006, became an official Mozilla project in 2009. Mozilla adopted it because they wanted a memory-safe language to write performance-critical components of Firefox in. Had a first stable release, version 1.0, in 2015. And this is really when you see the community begin to pick it up and start to run with it. Again, it was first used in Firefox. It's matured a lot beyond that point. It was designed as a system-level language comparable to C, even lower level than C++. So C++ has a bit of a runtime. Rust does not, and even the little bit of pseudo runtime it does have can be discarded. But the point is, in Rust, what you code is what you get. There's not something else that's sort of running alongside your code. There's no garbage collector. All memory is managed by your code, but it's all implicit and it's all guaranteed to be safe and it's all compile time checked. So even though there's no garbage collector and your code is managing your own memory, you also can't make memory issues with your code unless you explicitly break out of Rust safety features. You have to do a lot to break out of those features. You can basically compilation is targeting a CPU directly. It's not targeting a runtime. It's not an interpreted language. And this again to compete with C, there do have to be some language features where you can specifically say, hey, I want these CPU instructions at this point, right? I want this sort of single instruction multi-data CPU command that's only available on x86 with this instruction set. It is possible to do that kind of low-level thing in Rust, just like you can do it in C. So you can manually manage the kind of CPU instructions that your code generates. Nobody does that, right? Unless you are writing, the NumPy equivalents or translating from Fortran code or something. This is not something you do on a regular basis, but it's important because this means that you're unrestricted, and therefore, as a community, we can build code that really does what people that does what people need and what people want. And we don't have to say, well, if you want to do this kind of thing, you have to fall back to C. No, you basically never have to fall back to C. Speed is all important. I'm not going to dig into that. Looking at questions real quick, latency improvements rather than throughput for network I/O. Yes, latency is incredible for all these reasons. Fast cold start times, big deal. Auto scale with fast cold start times, big deal. Macros are hard. Yes, macros are hard, except in Rust. The syntax is a little complicated, but macros are actually awesome in Rust. And we'll come back to that. A little more in the history. That's fair. Rust macro, they are hard to write correctly, and the syntax is a bit complicated, but I'll still take them over C macros any day. We'll look at some examples of macros. Rust for Linux. So Rust for Linux is actually Rust replacing C code or being available language to write core kernel features or kernel drivers in the Linux kernel. This project was sort of conceptually launched in 2020. In 2022 was the first actual piece of Rust code that was added to Linux, or at least the Rust build chain, so people could. This was the enabling groundwork such that people could write Rust code and have it integrated into Linux kernel. The first actual Rust provided features came out in version 6.4. There's also this whole Redux OS thing, which is an entire kernel and operating system written purely in Rust. So file system, desktop, window manager, threading, kernel, everything. Top to bottom rewritten in Rust. Obviously, it's not a competitor with Linux or anything, but it's more of a proof of concept, but it shows that you can. And there's also Rust is great for embedded applications, so robotics, avionics, manufacturing, stuff like that. Adoption. So it's been around for a little while. How is adoption going? So Google internally did a big survey of thousands of its developers who had picked up Rust for the first time and started trying to contribute to real internal Google projects. You can see the pie chart in the bottom left where most people felt like they were able to go from I've never written Rust before in my life to I'm writing Rust code and contributing to an actual Rust project and it's working, right? I'm getting past code review. I'm a useful developer on this team now in under 1 to 2 months. Some people took a little longer. It's not a super quick language to learn, but this is not ridiculous in terms of picking up a new complicated language. More interesting, actually, than just they could pick it up in a reasonable amount of time. 3/4 of them were satisfied with the quality of their Rust code. And specifically, 85% were more confident that their Rust code was correct than any other code that they had written. So yeah, they're learning Rust for the first time. They're writing it for the first time. They're contributing to these new projects that they haven't contributed to before. But the very nature of writing Rust made them extremely confident that by the time they had written it and deployed it, it was correct in ways that in ways that they didn't get from the other languages that they had written in the past. And more than half the respondents said that the code is incredibly easy to review. Again, for fairly similar reasons, because so much is handled by the language that by the time it gets to a human reviewer or runtime, there's really not as much room for error anymore. Rust users famously love Rust. Ever since 2016, the year after it came out, basically, it has topped the Stack Overflow surveys for most loved language every single year running for, 8 years now. It's also been a highly desired language for quite a while now. You can see in the 2023 and 2024 surveys, the little blue dot on the left is basically how many people say, I would like to learn Rust. I would like to start using Rust. And it's been like top 5, top 6 languages that people want to learn and use. And it just, people really want to learn it. And once they learn it, they're like, wow, this is incredible. And yet adoption's been a little middling. This is GitHub stars on projects based on language. You can see Rust on the bottom, C in the middle, C++. Obviously C and C++ are absolute monsters to compete with. So am I surprised that Rust hasn't surpassed the two yet? Not really. But the trajectory is a little more even than I would have expected. I would have expected, for all the love of Rust, to see a little more adoption. And this is kind of a trend in the industry that people who use it love it, but it's kind of hard to get people on board to actually use it. So we'll talk about that a little bit as well. In response to that trend, what's my goal here? My goal is to commend to you that Rust is worth learning. I can't teach it to you in 2 hours. You can learn it. I think you can learn it in a spare weekend, at least get sort of the basics down. So my goal is to get you unscared, to convince you that it's cool. The complexity is there for a reason. It's worth understanding, for a wide variety of reasons, and that you should invest the day or two of time it takes to learn the basics and put this tool in your toolbox, even if you're going to have to kind of come back and learn it again later. I'm also going to provide the motivations for why that's worthwhile, and then some links to help you take those initial first steps. Okay, so what sets Rust apart from C and C++? There are two goals: speed and safety. C and C++ set out to achieve speed. They do a good job with that. Neither of them set out to achieve safety. They do a very, very, very bad job with that. So memory safety. This is kind of the really big differentiator. Memory safety without garbage collection. Why? If you've ever written C and C++ before, I 100% guarantee you've encountered a seg fault. A seg fault is any time that you perform some illegal memory operation, and your entire program immediately balks on itself. And if you, the only reason you do not blue screen your operating system and crash your computer and brick your CPU is because the operating system designers and CPU designers have done a good job of protecting themselves from your idiocy. Yeah, it's just, and the problem is memory-related bugs. The memory-related bugs are the historically biggest class of issues. SSL problems, HTTPS problems, web browser problems, just almost every bug. I think it's legitimately 70 to 80% of all security vulnerabilities in the past decades, probably 30, 40, 50 years, have been memory related. Basically, they were avoidable in the sense that it was not sort of part of the protocol. It was an error in the implementation, an error in the C and C++ code in the way that they managed their memory. Rust's goal is to give you all the same functionality that those other languages did, but without giving you the option to screw it up in terms of memory management. A really interesting side effect of this is that the things that you do to ensure memory safety also basically guarantee thread safety. And so whereas in a lot of other languages, you often sort of write your code single-threaded at some point, say, I need more performance, and then you have to basically go back through your whole code base and say, okay, how do I thread safe my code? In Rust, unless you did something strange, your code is probably thread safe by default. And that means that threading is a super common thing where a lot of Rust libraries are just like, oh yeah, flick this feature on and you've got multi-threading. Basically just comes for free a lot of the time, which helps with the performance. Also, safety is achieved without cost to runtime performance. Normally, we do things like garbage collection. That's a runtime feature that gives you memory safety. That has a performance cost, a performance impact. So Rust attacks this with zero cost abstractions instead. Safety is achieved at compile time, not at runtime. Obviously, there's no such thing as a free lunch. So what does, if your runtime is fast, that means your compile time is going to be slower. There's also a steeper learning curve with this. I'm not going to say it makes this programmer slower. I think the programmer ends up being faster, but it does make the learning curve very steep, and this is why. So when you're first learning Rust, there's this activity that you go through with the compiler called fighting with the borrow checker, and it's a hard part of learning Rust, but it's worth going through. So here's a simple, very, very, very simple example. Top code block is C code. We create some memory space on the heap for an integer. We throw an integer on that. We pass that pointer to a function, and then later we'd like to do something else with that. Maybe print out the value. Got a seg fault. Why did we get a seg fault? Look at that code. There's nothing wrong with that code, right? except that you've passed a pointer to a function, and that function could have done anything with the memory that that pointer points to, including freeing it, throwing away the allocated heap space. And maybe they threw away your integer and stuck a string there. And now your string starts with a something else, and you do a print statement. Suddenly you've got some junk data in your integer pointer. The above C code is completely valid, and it will segfault on you. The bottom Rust code will throw a compiler error at you instead. You're not allowed to do things that are going to get you into trouble. And so the compiler catches you and says, now you've done something that could end badly. It's disallowed by my safety rules. So instead, you need to figure out how you're going to approach this in a way that guarantees that what you've done is safe and valid. How do we do this? This is a concept called ownership. Ownership and borrowing go hand in hand. So ownership says the values are bound to their variable names. Values are bound to variables. So in most languages, variables are basically pointers that refer to values. Pointers is often sort of a C and C++ term, but this applies just as truly to Java and Python too, right? A variable is a name that refers to something, but you can have any number of names that refer to that thing. So again, in like Python, I can say x equals 5, or x equals some list, and then y equals x. Now I've got two names, x and y, that both point to the same list. And if I mutate y, and then I go back and look at x, I'll see that x now has a different value. And that's, even in Python, that's garbage collected in memory safe. That still means that I'm not thread safe, and that I've broken a variety of safety issues, caused a variety of safety issues, because I've mutated the value that one variable points at via another variable, and there's no way to sort of manage that. In Rust, the variable x, when you create, here in this code sample, I create a list, a mutable list, and I assign it to the variable v. V as a name now owns that value and cannot, it can't just, you can't just replicate that naively without noticing. So the next line, v2 equals v, is not a second variable that points at the same value. It is a new variable that takes over ownership of the value that v used to point at. And therefore, if we try to use v, it's going to say, whoa, you've already moved the value out of v. V doesn't do anything anymore. You can't use v anymore. V2 is where you have to go to get access to that value now. So variable assignments do this. Also, other kinds of variable assignments, like passing a variable to a function as a parameter, does this. So, a couple common cases, stack-only values. Let's say you've just got an integer. Okay, that integer doesn't point to anything, and it's just a small bit of memory. Can I have references to values too? Yes, you can. We'll come to references in just a heartbeat. So if it's like an integer that's 4 bytes on a stack, and I want to create another variable that has the same value, the compiler knows, okay, we don't have to explicitly say copy this every time. Just create a new value, x equals 5, y equals x. Okay, I don't have to move the ownership of 5 into y. I can just create a new integer called y and copy the value into that space. And as long as you're sort of dealing with stack-only values, if you don't know what I mean by stack versus heap, don't worry about it too much. Very, very simple, like primitive values, a fixed size. As long as you're dealing with that, it'll just copy memory around for you without making a big hassle about it. But it's important to know, because now x and y are two separate variables that point to two separate values. They're not pointing at the same 5 in memory. They're pointing at two different 5s in memory. That's safe. We guarantee that value mutations always occur through a single owner. That means that we don't have to, by default, by definition, we don't have to sort of track who, we don't have to have a separate concept of ownership. Ownership is owned by the variable and dealt with by the compiler, not by something at runtime. Is the copy trait for function parameters set in the function or in the call? It's set on the type. It's set on the type and how you pass the argument. So it will be in the call. When you call the function, you define what you're giving up. And when you define the function signature, you define what you require. Ownership can be passed down, can be passed both down and up. So you can pass you can pass ownership into a function, you can pass ownership back out of a function. Boy, that's going to get tedious if we want to pass around a bunch of read-only. Like if I want to give you ownership to read some values out of a struct, but you're not actually going to mess with the struct, then you still have to return ownership back to me. And that's, boy, that's going to get ugly. Sure wish there was an easier way. Oh, hey, there's an easier way. Ownership can be borrowed and returned. Rules of borrowing. Borrowing is what's called references. I'll show some code examples of what I mean by this. But just think of this like a library, right? The library owns the books. You may borrow the book. There are two kinds of borrowing. Read only. I borrow the book to read it, and then I'm going to give it back. Or mutable. I'm going to borrow the book, and I'm going to scribble something in it, and then I'm going to give the scribbled in book back. Yes, the borrow checker. This is the borrowing that the borrow checker enforces. That is the Rust learning curve. So these sets of rules that we're about to go through. Ownership and borrowing and references. This is what gets hard because we get so lazy in every other language, and Rust doesn't let us be lazy. So think of it this way: if I'm going to borrow, let's go say of Mice and Men. I'm going to go borrow of Mice and Men from the library, and I'm going to read it. And I promise when I borrow it that I'm not going to scribble in it. The library then, if someone else comes and asks for the same book, as long as they've got, let's just say this is a library that has their own printer and they're allowed to print out these books, they can give you another book, right? You're both going to be looking at the same data. Yeah, so as long as we're all going to read the same book, it doesn't matter whether I got the first print and you got the second print, or I got the second print and you got we're going to read the same thing. We've both promised not to write in it. And so it doesn't matter how many copies the library hands out, we're all going to see the same data. Those are read-only copies. The other option is a mutable copy or mutable borrow. So here I say I'm gonna borrow the book, but I might write in it. Now, if the library wants to make sure that everybody reads the same book, that is, memory is consistent, they need to not loan out that book again until I've given it back in and they can see what I've written in it. So these are the two rules of borrowing. At any point in time, you may have only one of the two following kinds of borrows. And sorry, I guess I'm talking to the next slide already. I'll go here. Did I? Wow, I'm getting ahead of myself. Oh no, it's point number 2. You may have an arbitrary number of read-only or immutable borrows, or you may have a single mutable borrow. So mutable borrows is sort of a delegated ownership for a short period of time. Additionally, borrowing cannot outlive ownership, right? I can't borrow a book from the library and then sell it. If anybody's going to sell the book, it has to be the library. They're allowed to sell it to me, and then I can sell it to someone else. But I can't borrow it. I can never sell something that I've borrowed. Ownership is retained. It can just be lent out via these borrows. So that's a fairly simple set of rules. A borrow must last for a scope no greater than that of the owner, and you may have at most one of the following kinds of borrow at a time: an unlimited number of immutable borrows or one mutable borrow. Notice that you cannot have both a read-only borrow and a mutable borrow at the same time. You can only have one of those at a time. You can pass along borrows. So if I've borrowed the book from the library, you can borrow the book from me. That's fine. You just have to give it back to me, and I have to give it back to the library. So we can delegate borrows, but this is still distinct from ownership. So I can't permanently give away a borrow. I have to be the owner of the variable in order to give it away permanently. This is important for thread safety. Yes, this is why it's frustrating. It can be frustrating to have only one type of borrow at a time, but if you submit to these rules, you are guaranteed memory safety. It also gives you thread safety. So let's consider a few common examples. Mutating collections while you're iterating over this. You can do this in Python, right? For x in my list, if x meets some condition, remove x from the list. Seems okay, except that the thing I'm iterating over is actually a data object that's pointing at my list, and when I remove something from the left side of that, I run the risk of skipping items, or I run the risk of running too far and iterating off the end of my list. Um, the process of iterating over a collection has to borrow the collection, and mutating it has to borrow the collection in order to mutate it. So in Python, even though Python's memory safe, if you mutate a collection while iterating over it, you get weird behaviors. It's not necessarily undefined; it's just bad. And it's generally a bad behavior that if you did that kind of thing, you probably weren't paying attention. You didn't know what you were doing. You probably screwed it up and did it wrong. Your code's now buggy. In Rust, the iteration is a immutable borrow. The mutation is a mutable borrow. Those two can't coexist at the same time. And so the memory model forces you to figure out, okay, do I need to copy my list first, or what do I mean by mutating the collection? Maybe I save it off into a new collection and I'll swap my collections later. But you have to choose you have to choose a valid behavior rather than just being allowed to do something stupid and wrong. In Python, you can. You can also have mutable default variable or mutable default arguments that have sort of a similar behavior where you can mutate things in weird ways and not realize it. Use after free errors. This is really a C++ thing, but this is similarly prevented because a use of a variable requires ownership or borrow, and freeing consumes ownership of that variable. And so it's impossible syntactically to free something and still retain ownership. And therefore, if you don't have ownership, you can't do anything with it. Therefore, it's safe because you're not allowed to do dumb stuff with it. And most thread safety issues fall into the same kind of thing. Ownership has to belong to a scope. That scope has to belong to a thread. And unless you specifically opt into certain sort of mutexes or whatever, even global variables have safety around this because of the way that they function. Yeah, all this ends up being very, very safe. Here's a wrong example. So I create a variable x, I give it the value 5. I create a mutable reference to that variable called y. So y is now a pointer reference that's allowed to change the value of x. And I modify the value of x by adding 1 to it via this mutable reference y, and then I try to print out x, but I can't. Why can't I? Because x is being borrowed right now, and therefore I don't have exclusive ownership over it. And I can't borrow it immutably for the sake of printing it because I've borrowed it mutably already. So this is a compiler error because y still exists. Y is still capable of mutating x, and therefore I'm not allowed to use x until y goes away. So you can do this safely, as demonstrated below, by explicitly defining the lifetime of y such that I say, hey, y goes away, I regain ownership of x, now I can use x again. Obviously, there are much more complicated examples. This will come up again over and over again as we kind of go through more code examples. Lifetime. So stuff has a lifespan, right? Stuff has a scope. Even Python, Java, we generally think in terms of scopes, but even then you can return objects up into higher scopes. I can create an object in a method and then return it up to a caller. Generally, lifetimes are not things that we think about very much. They're often implicit in scopes, or they're in C and C++. They're sort of managed via malloc and free and stuff like that. Because Rust is very intentionally needs to be aware of when things come into existence, when they go out of existence. We have a little more explicit concept of lifetimes, and especially we can name those lifetimes. We generally don't need to. We actually quite rarely need to. But sometimes we need to, and sometimes it's quite useful that we can. For example, I might want to create a struct or a class that stores a pointer or a reference to some other data. If I do that, I need to guarantee that the struct does not outlive the pointer. Right? If someone else frees my pointer out from under me, I have to have already gotten rid of my struct, or else my struct now points at invalid data. So I can bind the lifetime of my struct to the pointer that it's containing. And now the compiler can check and verify that by the time ownership of the reference is regained by someone else, the struct must have gone away already. I can just define that nice and concretely. Similar concept where we're creating data and then handing that back up. So if I'm creating an instance of an object or instantiating a struct on the heap or whatever, and then I hand that reference back up, this is basically what every constructor in existence does. I'm able to talk about the lifetime of that object if I need to. Generally, I don't need to. Some common situations, strings, constant strings. In C, does anybody know where constant strings live in a C compiled program? If you dynamically create a string, it's generally either in the stack or the heap. But if it's a constant, especially if it's a constant under some length, it's actually compiled into the binary. And all pointers to that string are pointers to the binary file in memory. So that they're not memory owned by either the stack or the heap. They're basically part of the program itself. So how do you describe the lifetime of that? Rust has a specific name for that kind of thing, for values that exist independent of the runtime of your application. Another interesting use case is parse without copy. This is a weird one. But let's say you get a binary stream of data over the network from some TCP socket or whatever. And you say, hey, I expect it, TCP has this kind of struct, and within that I've got HTTP traffic, and so that has this kind of structure. The way that you would do this in a higher level language is you would say, okay, parse out this binary data, copy it into a class. In C and C++, you can do a really high performance thing where you basically define the memory layout of your struct and then simply assert, hey, this random binary data I got over the network happens to be exactly in the right memory layout for this struct. Just create a pointer. Just pretend like this binary buffer is actually a pointer to my struct and start pulling values out of it like that. This is really high performance because it means you never copy any of the binary data. You basically just assert that binary data happens to be the correct memory layout for your data structure, and you move on with your life. There are cases where this is safe, and when it's safe, it's incredibly performant. Rust can do this, but how do you do this safely? And you do this with lifetimes and ownership, where basically the struct can borrow the binary data, the binary buffer of data that you got over the network, and assert that, hey, I recognize I'm here, but my lifetime is bound to that of the buffer, right? In order to free the buffer, I have to first free the struct that is borrowing and pointing to the data in that buffer. These are really, really niche use cases. Again, lifetimes don't come up super often. But the fact that you can do these kinds of things, again, means that you never have to, for performance or whatever, you never have to opt for an unsafe language. You don't have to fall back to C or C++ to get performance. You can do it in Rust. Not really that interesting for those of us who are kind of coming from Python for the most part, or Java. This is not the kind of thing that we generally worry about. But it does come up occasionally, and just want to explain the reasons why, because when it comes up, it can be obnoxious, especially having these like generic looking parameters. What does that mean? It's good to be aware that this is a concept in Rust. So here in this code example, we create some value 5, we create a reference to that, and then we pass that reference into the struct. Baked into this lifetime, this apostrophe A, it says that the lifetime of the struct cannot outlive. It must be less than or equal to the lifetime of this pointer. There was this reference that we had to it. And so the compiler is now able to guarantee that this code that uses that struct and whatnot adheres to those lifetime guarantees. And the result is memory safety without garbage collection. Immutability. This immutability often comes up more in conversations about like purely functional languages. It tends not to be very practical in a lot of real world cases. Like you just can't make everything immutable and get good performance out of it. But there are a lot of cases where immutability is great, and immutability is often perfectly safe. Create some sort of an error message. That error message doesn't have to be immutable, right? I'm just going to print it out and then throw it away. So immutability, meaning variables and values in general cannot be changed, is just the default behavior, and it's very easy to opt back out of that. This actually turns out to be really cool. One, because it results in simpler, it makes it easier to think about your data in your memory, the variables that you have, because in general, unless you specifically said I can change it, you can't change it. That means it just is, this variable just points out a value, then you know that that value remains constant, unless you specifically said it doesn't. Defaulting to immutability also enables a lot of compiler optimizations. These are things that you don't have to think about much, but it means that the compiled program and the compiler has much stronger guarantees about what is and isn't happening with your data as the program goes along, and it's able to do a lot more optimizations that results in faster code. And so this is just the thing that it's not hard to opt out of it when you need mutability. It makes it easier in general to think about your variables, because in general they aren't changing out from underneath you. And it results in faster code in general by default. Both borrows and bindings can be mutable. I don't think I'm going to dig into that a whole lot. But there's a couple places mutability can occur. It's either sort of the type of your variable, or the name itself can be mutable. So here's an example. In the first case, I create a variable called x, and then I want to change the value of that variable from 5 to 6. This is a compiler error. It's a compiler error because I did not say that x was mutable. So the second code block says, well, okay, I can just define x as a changeable variable. And now the compiler lets me replace the value that variable points to. Another thing I can do is just create a brand new variable with the same name, with the new value. Now I've got the first x with a value of 5, and then when I create the second x, the first x gets thrown away, the lifetime of that one ends, and I create a new variable that points at 6. How this actually works in terms of like stack and heap memory is a different question. But the point is basically you can choose what works best for you. And in general, the sort of this stacked like immutable assignment, immutable assignment, immutable assignment, if that works, you're going to get better performance out of that kind of code because you're providing stronger guarantees to the compiler. And it also makes it easier to reason about what's going on at any particular moment. Okay, types and traits. Rust follows more of sort of a C-ish concept. If you understand system level programming, you kind of understand why. So we don't have classes, we've got structs. Structs are associations of multiple values with each other, right? I think I have an example down here. So right here, we've got a struct that's a circle, right? A circle has a position and a radius, right? Not that complicated. You can nest these however you want. It's all the stuff you're usually used to with structs. What's important is that structs don't carry code around with them. They're just sort of blobs of memory, structured blobs of memory. And there's a few different ways of defining these. You can define them with named entries. You can define them with positional entries, like tuples. And you can even create empty structs that are basically types that have that are zero size in memory. Those are mostly useful for sort of compiler passing stuff around in your language without actually passing data around at runtime. You can attach functionality to structs, but you don't define functionality within structs. So in a Python class, you define your constructor, you define what class variables this thing's going to have, and then you define a bunch of methods at the same time. Same thing with Java. JavaScript is its own weird animal. Even C++ classes kind of do this, if I understand correctly. Rust is different. You don't. A class doesn't define its own functionality. Class is just a blob of memory, and then you can add arbitrary functionality onto that. If you've done a lot of C programming, this is going to be very, very familiar as a concept. In C, it's much more common where you'll have you don't have methods, you only have functions, right? And the first argument to a function is usually the data structure you're working on. So I might have like an image, and I'll have a bunch of functions that let me do different stuff with images. And every single one of them is the first argument is some sort of a pointer to the image data. In Java, Java, C++, and Python, we have this concept of self, this, that sort of implicitly takes that place. Rust kind of provides uh, the problem is that there's compiler issues if you go down that route, and so Rust avoids those issues by attaching methods, attaching functions to classes, but you still get this concept of self that is a nice convenience. It's just syntactic sugar, but it's a nice convenience anyway. That was a little rambly. I'm not going to go much into that, but this idea of attaching functionality. Formally, the concept is called composition rather than inheritance. We're going to dig a lot more into that in a second and why this actually turns out to be super cool. So, example, here's what you would think of as a C class or a circle class. So I define what data that class is going to contain, and then I define what functionality goes with that. You can see I've got this concept of self. It still feels very similar to classes in Python or Java, but syntactically it's two different concepts, the data and the functionality getting attached to that data. Before we get too much further into that, let's talk about enums real quick. In Python, and I think I'm not so sure about Java. At least in Python, enums are usually names attached to values, often like strings or integers, and they exist mostly for sort of saying, hey, I can have three different colors: red, green, and blue. Red equals 0, green equals 1, and blue equals 2. Right? Whatever. In Rust, enums are names attached to types. The enum itself is the top level type, but each variant is a subtype. And again, we'll come back to why this is super cool. We can get sort of the same name attached to value behavior if we want. I'm not really going to show that, but it's pretty easy to do. But let's say I want some sort of construct of an HTTP color. Well, in HTTP, a color can be defined in a few different ways: 3 integers, red, green, blue; 4 integers, red, green, blue, alpha; hexadecimal string, or a predefined name, orange. In Rust, I can define a single enum that's just HTTP color, and then define 4 different variants, one for each of those different possible ways of describing a color. And I can now refer distinctly in my code to, okay, all of these different things are creating HTML colors. I've got one sort of functionality attached to HTML colors, but I can still let the user, when they're passing data in, pass in that HTTP color or HTML color in any way that they choose, whichever way is most convenient for them. So here's maybe an example. This would be some sort of like a message passing system, maybe in like a game engine or whatever. There's a variety of messages that can get passed. Maybe I want to quit the application. Maybe I want to change the background color. Maybe I want to move my character around, or I want to print some message to the screen. All of these are possible messages, and I want to be able to define, like, hey, I just have sort of some sort of a system that lets me send messages and a system that lets me receive messages. This lets me define all that in one place. So I've got a single type that is what people are sending and passing around. And then at runtime, I can sort of say, okay, now which one of these am I dealing with, and how do I handle them each individually? All right, let's come back to the whole functionality. Composition versus inheritance. So in Rust, types are composed. In Java, Python, a lot of other object-oriented languages, types are inherited. Top down versus bottom up. So in Python, you've got stuff like base types. This class inherits from this other class. You've got abstract types that are classes that are not supposed to be instantiated by themselves. They're only intended to be extended by other classes. You've got this concept of interfaces, which is sort of like a class, except it's not at all. Sort of just defines what other classes ought to look like. And when we build a type, we have to smash all these things together in the correct possible way. And then we can't really change that after the fact. So each of these foundational concepts of base classes, abstract types, whatever, infer something about what our class should look like, and then when we define our class, we have to live up to all of those expectations all at once. And if we ever want to add functionality, we've got to create a new type that inherits from that type and adds the new functionality, right? It comes, everything is defined when you define the class. So this is kind of what I just talked about. Let's say we've got like a NumPy array. That's module A. And then we've got something that says, hey, NumPy arrays really ought to have this other function over here. This is module B. Maybe this adds some ability to convert NumPy arrays to pandas data frames. And then we've got some module C that says, okay, I don't know anything about pandas, but we should be able to convert NumPy arrays to CSV files. Cool. And they both want to add functionality. Well, in module B, the only way to do this is to, in general, forgive the example, it's not a perfect example, but we would generally do this by creating some sort of like a NumPy array, custom NumPy array class that has the additional functionality that we want. So now we've got B's custom version of a NumPy array that has additional functionality. C creates its own version of a NumPy array that has its additional functionality. And now you're writing a library and you want to use both of these functionalities at the same time. What do you do? If you're lucky and the language is good, you can create a fourth type called D, where you create my own custom special version of NumPy that nobody else has, that inherits from both B and C and smashes their functionality together. If you're unlucky and B and C were defined badly, you can't. There's just no possible way, and you have to sort of like convert back and forth between B and C's custom types, and just sort of hope that everything goes fine along the way. So this, in traditional object-oriented programming, you kind of have this struggle of, I want to add functionality, but I don't want to fragment the ecosystem into custom types, and you end up with lots of weird behaviors and things that people do in order to add functionality to existing modules without fragmenting the ecosystem. In Rust, that's not the case. And there are other languages that do type composition. It's not just Rust, but this is a really cool approach where instead we define a type in A, B and C can define behaviors, and then implements those behaviors against the existing type that comes from A. And then when we're writing our code in module D, we can just say, import the type from A, import functionality from B, import functionality from C, and just use them all. No custom, no derived types, no inheritance, no nothing. And the compiler and type system and the way the syntax works guarantees that we always know what we're talking about and that B and C aren't capable of referring to each other unless they specifically tried to. So even if they use like same named methods and whatnot, those methods are still namespaced to those modules and to the traits that implement those behaviors. And there's no possible way for them to collide with each other. So here's an example. Let's say I create some sort of behavior called shape. I'm going to have a bunch of stuff that all behave like shapes. And every time I've got something that behaves like a shape, it needs to do two things. It needs to be able to give me an area and a parameter. I'm going to go implement two different kinds of shapes, one called a square, one called a circle. And then I'm going to implement this behavior for each of those types. So for a square, I implement area and perimeter. For a circle, I implement area and perimeter. So the previous example is sort of what you're doing if you're in one piece of code. How do modules interact with each other? There's a crate or library called itertools. It's a really awesome example of this. So itertools is basically adding a bunch of iterator functionality to existing data structures. So these are all built-in Rust data structures. You can use these whenever. So we've got, down here we've got our vector. This is just a array of changeable size. This already provides lots of nice rich functionality. That's great, but it doesn't provide everything we might want. And so the itertools library says, well, I'd love to be able to provide more. What it does not have to do is it does not have to provide its own version of vector in order to provide this behavior. Instead, it implements a bunch of traits and then implements those traits against the built-in vector data structure. And so when I've got this built-in data structure here, I've got this built-in method here that comes from the built-in library. And then I've just got this extra method here provided by the itertools crate. So I'm able to attach functionality via either in my own code or via third-party code to pre-existing functionality without the pre-existing functionality to have any awareness of the fact that I'm doing so. And this is all safe to do. It's the guaranteed safety structures are quite strong. Some cool advantages of this is that libraries, it's really hard to make two libraries incompatible with each other because of the safety guarantees around all of this, which often means that you don't have to know one library in order to learn another. For example, in order to learn pandas, you have to understand NumPy. Because it extends on NumPy, it depends on NumPy and builds on top of it. And that kind of thing just doesn't happen much in Rust. In general, functionality is attached to concepts, and they just work with each other, and you can often import lots of different things that all expand on the same concept without having to sort of decide. They don't have to know about each other, be compatible. They're just by default compatible. And it also means that it's really not all that common for crates to have to define their own data structures in a lot of ways. Instead, you end up with sort of a small number of data structures, those that are built in and maybe from a couple other packages, and then a lot of libraries that expand the functionality of those data structures. And this really decreases the long-term learning curve because it means that you can build better and better and faster code that uses more and more third-party tools without leaving the data structures that are there from day one. That's sort of a normal common concept. Let's talk generics real quick. We can define types in terms of other types. If you've used any object-oriented language, you're familiar with generics. This is not a new concept. There are nice syntax features around, okay, I'm going to build one type. It's a generic parameterized by some other type, but I'm going to assert certain functionality about that other type. There are basic features. Again, this is not really earth-shattering. If you come from C++ or Java or even to some degree Python, this happens. And this makes it easy to define structures and enums and other data structures that wrap other data structures. So here's a struct that's like, hey, I just want to take something and add. I want to be able to take any value in memory and attach a description to it. Maybe I do this so that I can do some sort of reflection-based description of what's going on in my application. So I can create this structure that says, hey, I'm going to store something and also a description attached to that. I have no idea what the something is. I don't really care. None of my functionality is going to depend on what that something is. I'm just going to contain something and attach a description to it. Cool. A really common use case of generics is this idea of like option, where I could say, hey, maybe I've got something, maybe I don't. Right? Now I can define that as enum. Enum has two possible variants. One is the none, which is an empty zero size data structure, and the other is a sum that is just a type descriptive wrap around the fact that I've got something. I don't know what that something is. Again, I don't care about it. It's just some data of some type. Let's talk about this option thing. So there's two built-in enums that are generics that come up a lot in Rust, option and result. Result is the concept of exceptions or errors. And so result is just an enum that can be either in an OK state or in an error state. And this is the way we pass exceptions around Rust. What's cool about this is that it means that exceptions are just data. They're just data in your application memory. They're data with nice strict type definitions around them, which means that the compiler can check. What this means is that you cannot raise an exception basically from one function and fail to catch it in the next in the function that called that one. It's data. It's part of the type system, and therefore, if I got something that could have been an error or could have been okay, I have to actually check on it. I have to deal with the error state and unwrap the okay state in order to get at the data that got returned. And if this you can implement this yourself. It's really not hard. It's just an enum that has either a value type or an error type as generics, and two possible states that wrap those. So here's an example of what a typical fallible, that is a function that can fail, what a typical fallible function would look like. This is like a square root function where I say, hey, if it's a valid number, then just compute the square root and say, yep, that worked. And if it's not a valid number, then I, crash cleanly. And the whatever code calls this function then has to take whether did I return an OK or an error, and they have to look at those and implement both cases every single time. You simply cannot write a valid compilable program that does not resolve the fact that it could be either an OK or an error. And this means that error handling is ubiquitous. All code and all Rust handles all errors basically all the time. There's only one exception to this in terms of panics. I'm not really going to get into that a whole lot, but basically the normal way programs are implemented, every exception is handled all the time in some fashion. And this is implemented via generics and enums. Same thing for nullability. There's the guy who invented the concept of null has been spending the last 40 years apologizing for doing so. Refers to it as his $1 billion mistake. The fact that so many of our languages let anything possibly be null by default has been an utter catastrophe of language design. In Java and Python, you can often, this just results in nice runtime exceptions. In C, if you deal with a null pointer, that's a segfault, and suddenly the whole thing catastrophically fails. The idea that stuff cannot be what you expect it to be, that I can say, hey, I want an integer or, some sort of a class, and it can just not be that all the time, is an absolute train wreck of language design. And so when Rust came along, they said, well, this issue is a root of all sorts of evil in programming. Let's not have it. And instead, we have this this data type, and this data type encapsulates logically as a type in the type system whether something is nullable or not, and whether that an instance of that is null or not. And again, just like results, you have to always, anytime something could be null, you always have to deal with both possible cases. You can't just get at the value and move on with your life. You have to define what you do, define what the behavior is if it were null, always, all the time. Something cool about the way generics work in Rust is that you could define the generic in terms of types, or you can define the generics in terms of behavior, so as traits. So you can say anything that looks like this, any struct that has this trait implemented for it, is a valid type parameter to something else, whether that's to another struct or to another trait. That sounds super weird. Let's take a look at a concrete example. Let's say I've defined the concept of a shape. A shape has an area and perimeter. And somewhere down the line, whether in the same package or in a different package, I say, oh, shoot, I really want to be able to I want to be able to describe anything that has the concept of a surface to area ratio. That might be a shape, it might not be. There might be stuff that aren't shapes that still have surface area ratios. That's fine. But if it is a shape, and that's what's going on here, if I have something that is a shape, any type that implements the behavior that I expect from a shape, I can implement surface to area ratio for that type using this simple equation, right? You might implement surface to area ratio some other way for some other type. That's fine. But this is the way it works for everything that implements shape. A safety guarantee is anything that has this implementation available cannot also redefine a different way to compute surface to area ratio. The compiler will guarantee that every type has at most one possible implementation of this trait. And if it's even theoretically possible that a type might at some point in the future gain a different implementation of this trait, then you can't do it. And so it's just lots of really strict guarantees to make sure that this kind of super flexible behavior, just always implement this trait for all other things that implement this other trait, still guaranteed memory safe all the time, forever. All right, let's talk about macros real quick. I know this is all a lot. Again, I do not expect anybody to walk away from this being like, yes, now I can write some Rust code. My point is to sort of drive home like this approach to composition, this idea of using traits, this idea of structs, the way they've done this, they've really thought through this in very concrete and safe ways, so that the result is a very usable language, a very powerful language, and a very sort of principled language. And these are good ways to approach the problem. Yeah, if you can walk away reading Rust code, I will be honestly, even then I'll be impressed. And yeah, there's. I'll say the one downside I've seen with traits is it tends, because you're able to syntactically separate implementation from data, it can often be really hard to figure out, hey, I've got this method available on this data structure. Where on earth did that method come from? Where is that code? If you've got a good IDE, of course, it's always deterministic. You can always sort of control click and go find it. But just sort of skimming through the code, it can be really hard to understand what functionality is available for a given piece of data, because that functionality can come from so many different directions. Okay, cool. Let's talk macros. So a macro is code generation. That's just basically always what macros mean in programming. In C, the way you do this is you define basically a string-to-string conversion, text-to-text conversion. You define some macro that consumes some arbitrary C code and templates it into some arbitrary text, and then puts that arbitrary text back into your C code and says, haha, try to compile that. If you've ever done this, you know that getting it right is incredibly hard, and all sorts of errors come up. And it's just incredibly easy to abuse these. It's incredibly easy to use them wrong. It's incredibly hard to write a macro that is safe. If you look at even simple macros, there's often when I've written C code in other contexts, people have macros for sort of their approach to handling errors. And the actual definition for these macros is just mind-numbingly painful, because they're safe. And getting safe string-to-string conversions of our C code is just a train wreck. In Python, we don't really often use macros per se. You can do code generation, but it's pretty rare. We do use the decorators a lot, and decorators serve a fairly similar purpose, where you of sort of eliminating boilerplate and attaching default behaviors, or expanding behaviors of certain things. So that comes up. But what's common is that the basic language and the type system and all that jazz don't always provide everything you need for every kind of application that you want to write. And often you want to be able to introduce ways of writing code into your code base that make your particular code easier to write. This is quite normal. And so this is where macros fit in, and Rust said, okay, we want macros. There's a wide variety of ways that you might want to write macros that are some are simpler and some are harder. But the one thing we need to know is that this needs to be safe. Writing bad macros is not a good way to go. So there's kind of two general ways of writing macros. One is what's called macro rules. Macro rules are macros by example. This is actually basically what you see in C macros. So somewhere in your code you say, hey, I want to define a macro. It looks like this, and it produces code that looks like that. So this is a fairly lightweight syntax that lets you define the vast majority of macros in a reasonably readable fashion. And it's generally described as macros by example, because the code that you basically write out here's the kind of code that it's going to look like, and then fill in some placeholders. Again, if you come from C or C++, this is what you're used to with macros. What's safe about them is that the inputs and outputs of macros are not text. It's not code. It's actually syntax trees. And syntax trees are typed. So you can say something like, I want an identifier. This would be something like a variable name or a function name or a class name, right? Or I want an expression. This could be x plus y or a function call or anything like that. But as in your macro, you say, hey, I want some sort of an expression, and then I can only use that expression in other places in my syntax that expect expressions. And what this does is it means that the compiler can check not merely that my macro has generated valid code, but that in fact my macro is itself valid code, even before I try to use it on anything. That is, it's guaranteed to generate a valid code. And then if I use a macro incorrectly, it can explain why. This expected an identifier and you passed an expression, right? Simply, I can't use an expression where an identifier is expected. It can basically type check the syntax in that sense. And another cool thing is because of this, because it's syntax tree to syntax tree conversion, rather than string to string, it means that this doesn't get in the way of static analysis or IntelliSense. So this is stuff like autocomplete. So I can actually, when I'm writing in my IDE and I'm inside of a macro definition, it's able to say like, hey, you passed in this variable, but that variable is the wrong type, right? And it needs to have this method. And it can do that because it's looking at how that code is getting passed in, what the resulting syntax tree looks like, and what are the expectations on that resulting syntax. I realize if you haven't done sort of language design or worked with syntax trees before, this is a really weird and abstract concept. But just to say it's checkable in a lot of ways that results in very clean behavior, not just from the compiler, but from other tools that interact with your code, such as your IDE. So it's guaranteeing safety, but it's also providing those guarantees in very practical ways. Some common use cases I've used macros by example for implementing the same kind of trait for a bunch of different types. Normally it's like a 5-line thing or maybe like a 10-line thing. Implementing a bunch of very similar types. It's very easy to sort of describe a macro, like this is the kind of code that I'm going to write 10 times, just to find out as a macro and then you call that macro 10 times instead. A really cool example is this is a cool library. It's designed to be a web front end, so this library is competing with React and stuff like that. I'm not gonna get into how it does that, but it defines this macro that you can then use, and inside this macro, you get a syntax and a behavior that feels like HTML. Right? You've basically created an entire domain-specific language with using macros, such that I can now describe, hey, I want to create sort of this HTML kind of document object model thing. I can just do that in a way that is familiar and comfortable. And then the macro handles all the complexity of unrolling that into valid Rust code that can actually be compiled and executed. Macros for constructors, yes, although constructors and such are actually pretty well defined in Rust, such that that's often not necessary. So, yeah. But yeah, that kind of thing, implementing very typical behavior repetitively. If you can't handle it with the type system or something like that, you can use macros pretty easily. But it goes further than that. You can write procedural macros. Procedural macros are entire Rust libraries, entire Rust applications that consume Rust code and output Rust code. And again, this is at a syntax tree level, not as text. So you can type check the whole process and guarantee that what you're consuming is always valid Rust code and what you're generating is always valid Rust code. But this lets you do anything you want, right? Arbitrary Rust code, arbitrary application that has arbitrary dependencies that can do code generation and code mutation. This lets you do really, really complicated things. This is really higher barrier to entry right now. People try to avoid writing procedural macros because they're pretty hard. And there are some ways they fit into the build chain that can be a little bit annoying. But you are completely unbound, right? Anything that's Turing complete in terms of code generation, you can do as procedural macros. All right, so that's macros. Again, I'm not really getting into examples because they tend to look really complicated, and you kind of tend to build one or two. and then just use them over and over again. They're not something that you're kind of constantly writing as part of your code. And it's all about sort of providing you compact ways of describing more complicated and convoluted syntax. It's just about simplifying your code, right? So I'm not going to get into too many examples of that. Okay, tooling. Let's talk about tooling real quick. So we've written all of our code, whatever. We've used types and stuff. Now we want to actually build stuff. We want to have dependencies. And if you come from C or C++ or even Java, defining your build chain starts getting to be a pain. This is probably one area where scripting languages have become quite nice, is that you basically build all that into the environment management. And when you actually go to run your code, it's just the environment's all sitting around ready to go. So you eliminate the whole build chain problem. Rust doesn't get to avoid the build chain problem. So instead, it just builds a really phenomenally good build chain. So it's got this tool called Cargo. Cargo you use for everything. Cargo is how you create a template for your project. Cargo is how you add dependencies. Cargo is how you build your code and run your code. Cargo is how you publish to the central shared registry of all libraries. Everything goes through Cargo. Even running unit tests all goes through Cargo. It's awesome. It's incredibly well built. Basically everything that you run into with other languages has at least been thought about when they wrote Cargo. All the linking, all that stuff is all handled by Cargo. If you come from C++, you know that linking is a pain. So in general, this scales to as complex or as simple as you need. If you want it to be simple, you can just run Cargo run, right? It'll do everything for you. It just says, oh, you want to run your Rust code? Great, let's do that. And it knows how to chain all the processes together to make that happen. This also includes the package manager. Rust has a world-class package manager. It's really incredible. It's learned from all the other package managers. So, heavily inspired by NPM, heavily inspired by PyPy. They learned a lot of lessons from a lot of other languages and did a very good job taking those lessons learned and doing good stuff with them. You can even customize the build process with, drumroll please, Rust code. There's a concept called BuildRS that lets you define Rust code that interacts with the build process. Yeah, Cargo is often a thing that people grind into Rust and are like, well, hey, like a usable language, like not just, they didn't just think about Rust, they thought about the usability around it too. Cargo is pretty famous across language design for being, they did a really good job with it. There's this BuildRS concept where you, and like C and C++, you have make or CMake where you have to sort of script your build process. And there are times when you need to customize something, right? Refer to an external header or, tweak something about the build code, or maybe do some code generation. I want to, take this protobuf file and render out the Rust code into this particular location. There are things that you need to do to customize the build process. In other languages, that's an afterthought. You build it on with external tooling. In Rust, it's part of BuildRS, it's part of Cargo. You can write your code as Rust, which means it's safe and part of the build chain and all that jazz. Yeah, really, really, really good build tooling. It goes all the way from, I just want to run my code, please leave me alone, to I need to do the most complicated things in the world. We got you covered. Including things, this is sort of the grab bag of stuff that you generally don't have to care about, but cross compilation. I can compile stuff and execute. I can compile stuff on my x86 computer and run it on an ARM computer on a regular basis. That's normal. LLVM under the hood, so they're not reinventing the wheel. They're using really, really good foundational tooling. Caching of all of its build processes and all the package management. Native support for multi-project, like monorepo stuff. So I've got a giant repo that has 5 different Rust projects in it. Great, we got that handled. We know how to take care of that. Dependency hell, largely avoided. I'm not going to get to the details of that. But it benefits from both sort of the approaches of like PyPy, Python, where you want to share versions of code, and also from NPM, where you can say, well, maybe these two libraries can't share the same version of the code. I guess they're going to get two different versions of the same library, but I'm going to guarantee that they're safe when they do so. This is just sort of a grab bag of language features. Closures, defining functions as variables that consume context around them. That's a normal thing. Async, not quite a first-class citizen. I know I haven't brought up Golang. I know if Neil were here, he would bring up Golang. Golang is also awesome. I'm not at all saying that should not use Golang for lots of stuff. In Golang, async is just like a core language feature, right? Async is the thing that Golang was designed around. Rust is not. But they've been thinking about async for a long time, and they've done a really good job of it. And it's quite straightforward to use for most things. Also, because Rust is inherently thread safe all the time, just by default, async and multi-threading often go hand in hand. So like here, I've got this Tokio. Tokio is a library that implements async behavior. And I think by default, I think actually in this code example, as shown, asynchronous tasks are already delegated to all possible CPU cores. And so if you're doing like web scraping or something and hitting a bunch of web servers and doing some processing and pushing stuff up to S3 and you're using async for all of that, just by default, it's all already multi-threaded and you're good to go. Not something you need to think about after the fact. Iterators are incredible. If you come from, I know C# and Java have sort of this iterator syntax. In Python, you generally use like list comprehensions. List comprehensions are like this, just more limited. This concept of I've got data structures, and I've got lots of different kinds of data structures, and I kind of want to do the same kind of iterative methods. I want to iterate over them, filter them, map them, change them, mutate them, a bunch of different stuff like that. All that's first-class citizens in Rust. Tons of really good functionality built in, and the way they've implemented it, because of how this all unwinds into types and traits and zero-cost abstractions. That's going to start becoming more of a theme. Even though the way this is implemented looks like I'm going to call a function, for every single item on my list, the way it actually unrolls in the compiler means it doesn't have to. If the most efficient way to implement this would be basically a for loop, then in the compiled code it will be a for loop, where this num times num code gets sort of inlined into that for loop. So tons of stuff that would normally be overhead in something like C# or Java unrolls very naturally in Rust because of the whole stack of zero-cost abstractions this is built on, and the result is as performant code as if you wrote it yourself. And so you can sort of use these nice abstractions and these nice methods without fear that you're throwing away performance in the process. Type reference is awesome because all of us who have written complex types say why. Duck typing languages just say, why define the type of things? And that is its own bag of worms. This is a strictly typed language. You do need to know the type. Everything has a strict type. It has to be known strict type at compile time. But that doesn't mean that you as a human should have to write that out every time. And frequently you should not have to. So type inference exists. It exists. It's very, very good. Here's an example where I create a vector and assign it to a variable. What's the type of that variable? Duh, it's a vector, right? I just told you, right? By the type of the right-hand expression, I can just guess what the type of the variable should be. I can define my types partially. So I can say, hey, it's a vector, but I don't know what it's a vector of. And the compiler will infer the missing pieces. Or I can specify things explicitly, right? So these first two lines are going to be a vector of I32 or isize. So whatever the native signed integer would be. On the third one, I specifically say it's always going to be a 64-bit integer, no matter the platform or what you might have thought I was talking about. So you can be specific. Notice that the third line actually reverses the type inference. So in the first two lines, it looks at 1, 2, and 3, says, hey, what type do I think these should be? They could be a variety of things. They could be a 16-bit int or a 8-bit int or a 32-bit int or a 64. I don't know. I'm gonna pick a safe default. on the third line, I say, hey, they should have been 64 bits, and it will actually reverse that type of inference and say, hey, when I see this 1, 2, 3, the only thing these can actually be is 64 bits. They couldn't have been something else to start with. So this type inference thing goes a lot of different directions and is really beautiful. Additionally, you can have sort of piecemeal type inference. So here I create a new vector of who knows what. Right? It's just a vector, and I assign it to a variable called x, and then I push a string into it. Oh, so it must be a vector of strings. Cool. And then I try to push an integer into it. Well, I thought you said it was a vector of strings, so now I've got a compiler error. Right? You tried to push an integer into a vector of strings. What's cool? Two cool things. One, the error message tells you this. It tells you its chain of thought. It says, hey, you pushed a string into this vector. That caused me to think that it was a vector of strings. But then you try to push an integer into that, and that's now got the wrong type signature because it's the wrong type of thing to push into a vector, into this particular vector. The other cool thing is, check out that ASCII art. Isn't that cool? Like, this is the actual error message. This is not like me doing something fancy. This is the actual error message that gets printed out by the compiler with all these weird squiggly pipe things and nice underlines and multi-line stuff. Like, when they set out to create Rust, they're like, okay, the one thing that we know is going to suck is the compiler is going to fight with you non-stop, right? That is going to suck. Everybody's going to have to go through that suckiness. So the one thing that we're going to have to do if anybody's actually going to use this is we're going to have to make great error messages. And so for the last 10 years, they have been just sinking effort into making the best possible error messages. And there are still tons and tons of issues on GitHub about improving error messages, not because they're bad, but because this is basically a first-class feature of the language, that error messages should be incredibly good. And they are. So I threw away a couple lines in this just for brevity, but this is what error messages look like in Rust. All right, immutability by default. We already talked about this a little bit, but immutability offers lots of compiler optimizations. Again, when we default to this, we generally get better and more sort of readable code and faster code too. Zero cost abstractions. Fundamental principle in Rust is you should never want to write a feature yourself just because the feature we provided doesn't perform well enough. So again, this is another thing where we offload complexity to the compiler so that we don't have to offload complexity to the runtime compiled code. So abstractions are complicated, but they're compiler abstractions rather than runtime abstractions. So that's important. And again, zero cost abstractions, it sounds like, okay, well, sure, like you inline some functions and you collapse some literals and whatnot, what's the big deal? But when you start stacking on top of each other, you start getting stuff like the iterator syntax we looked at earlier, where you get very readable code that through a whole chain of zero cost abstractions turns into very high performance code. And therefore you use you regularly use high level abstractions without sacrificing high level performance while you're at it. Okay, explicit nullability. Nothing can be null by default and nothing can be errored by default. So if something is possibly an error, then that's part of the type system. If something is possibly null, that's part of the type system. In both cases, you have to handle them explicitly. You can't just pretend like they're not null or assume they're not null. There are some syntax features that make this quite convenient. There's this nice question mark thing. I believe this shows up in like C# and a few other languages too. I'm not going to get into a whole lot, but basically it says, hey, if this was an error, raise an error. And so it's a very compact way of saying, pass this error along, but if it's okay, just give me the successful error. Same thing for nullability. If I got null, return null. Otherwise, let's work with the non-null value. But this is just syntactic sugar. This is not, there's nothing fancy going on here under the hood. It's just, you can, it's just syntactic sugar for data, data operations. We've already talked about this a few times, but exceptions are code and they're data. They're not a language feature primarily. There is this concept called panic. there's generally no good reason to be using panics. Calling panic is a lot like calling system.exit, where it just terminates the program. There is a traceback, so it's a little bit better. You can disable the traceback because the traceback feature has some dependencies that not everybody wants. But generally, you don't panic. Generally, you have exceptions. So here's like an example of making you're parsing a string as a URL and then calling that URL, getting the data, parsing out the JSON object to a particular type, and then taking a look at it. So there's a lot of areas that could go wrong, a lot of things that could fail in this pipeline. Also, notice the await. This is asynchronous code. And we just kind of don't have to deal with that. As long as you're sort of aware of what's going on and you define your type signatures properly, we can just basically stack all these question marks on top of each other. And at every point, it's like, if it fails, then the whole function fails, right? There's nothing I can do to fix that. Just propagate the error up. But it's still handled as data, and therefore it's still handled by your code. I've talked about tests and test-driven development pretty early on. So let's talk about that a little bit. I'll come back again a little bit more to this later. But tests are a built-in language feature. They are not some sort of third-party afterthought library. In Python, you want to do tests? Yeah, there's a built-in library called unit tests. It's kind of crappy. Mostly we go use PyTest. But those aren't language features. They are libraries. In Rust, there are language features and compiler features that let you do tests efficiently. These can be expanded by third-party libraries, but you don't have to. So one of them is like, hey, I can mark this code as test code. What this means is if I'm not running tests, I don't need to compile this code. In fact, this whole chunk of code just vanishes if I'm not running tests. I flag this function as a test. When I run cargo.test, it looks for all functions with this annotation on them and treats each one as a test case, right? To some degree, these are language features. They are language features, again, that can be replicated and mutated and changed and customized. But it's not like you have to figure this out on your own, or each library has to reinvent its approach to testing. So those are sort of what set Rust apart in the low-level languages. Let's take a look a little bit in sort of how Rust even competes with Python and high-level languages. These are going to be much more obvious and sort of more design decisions rather than like cool implementations under the hood. Starting with, it's just strictly typed language. Python is not. Python is typed in ways that like JavaScript is not. Values are typed, but the language itself is not. Variables are not typed. So Rust chooses to go with strict typing and use traits, use composition instead of inheritance. We've already talked about that a lot of times. This does make it harder to write individual pieces of code, right? In Python, you can just say like x equals 5. Well, maybe now x equals a list. Make x a dictionary now. Who cares? You don't have to think about that at authoring time because it all gets checked for you at runtime. What that means is that the language can't do any sanity checking for you because anything you wrote basically could be valid. It doesn't know. Strict typing lets the compiler take a lot of that mental burden for you, which especially as you start writing bigger and bigger code bases, having that mental burden offloaded becomes incredibly valuable. And the compiler and the borrow checker and the type system will raise errors for you and validate that your code is correct without you having to constantly go back and think about that yourself. Obviously, with strict typing comes, okay, but strict typing means inflexible, right? Duck typing I like because I can just flex. It flexes with me, right? It doesn't get in my way. So how do you do strict typing with flexibility? And that's where we get into a lot more Rust language features. So this is a lot of destructuring, match statements. There's some cool stuff around how you can break values out of other data structures. So I'm not going to really dig into this, just to say there's a lot of thought, a lot of clean syntax. Match statements are super, super awesome. and they do some really incredible stuff. And again, because they're a zero cost abstraction, you're not going to be better off writing this kind of branching logic yourself. You end up with a very high performance piece of code, but very high level syntax that lets you describe the kind of behaviors that you're looking for in a very readable fashion. Also, because of all the stuff that we've talked about, you get thread safety by default. There's a really cool library called Rayon that lets you, we looked at like iterator functions. So like take a vector, iterate over it, and do some operation on all its values. Rayon lets you insert a single line of code into that says, oh, and by the way, when I say do that, I mean do it on parallel threads. And it just integrates with it because of all the beauties of traits and all that jazz. It just works. Then your map occurs in parallel on multiple threads, which especially if you're doing things like hitting URLs or doing some CPU intensive work in your map function can dramatically improve your performance. Similarly, the Tokio libraries, the library that is one of the main libraries that implements async logic, and it runs all of your green threads on a pool of actual physical threads, and so it can take advantage of all your CPU cores as well. This is just super common, again, because Rust is thread safe by default rather than thread safe as an afterthought. As you expand through the Rust ecosystem, people will generally tell you when something is not thread safe rather than when it is. And almost always stuff is thread safe, and it's quite easy to take advantage of that fact, usually with very little changes to your code. Code generation is compilation of runtime. So again, Python doesn't really have a concept of macros. It does have decorators. Decorators are lovely, and I do love them as a Python language feature. But it's all a runtime burden, right? Rust moves that burden to the compile time, which lets it validate that what you're doing is actually logical and that it actually works before compiling your program, rather than having to figure that out when you actually run your program. Package management with that dependency hell. I am a very big Python fan. I think that's completely obvious at this point. But one area where it does begin to suck is dependencies. And in particular, what's called the triangle paradox, or the diamond paradox, I guess, where you depend on two different libraries, but those two different libraries depend on one same library, but two different versions of it. This is an unreconcilable problem in Python. Because every package is uniquely identified by its name, you can only have one package of each name in existence at runtime, and therefore if two different packages require two different versions of that same package, you can't do it. You can only have one version of any given package at a moment. And the dependency resolver just crashes, basically, or you have to resolve it yourself. Rust doesn't have this. It's able to pull in multiple versions of the same package if necessary. Obviously, that wastes compile time and stuff. So it puts in a lot of effort to avoid doing that. But if it's necessary, it can, and it can confirm that data structures and types and memory created by one version of that library never make it through the code back to another version of that library. And that's where dangers would come in if you did that. So it doesn't prevent every possible thing, but it does prevent dependency hell and do so relatively safely. Static linking. So Rust, unlike C and C++, generally does not build binaries that depend on external libraries. It is possible to. It's pretty frowned upon and kind of obnoxious because most Rust libraries don't do that. The downside of this is that your compiled binaries are quite large. In C, you could build a program that's 10 kilobytes big. In Rust, you build a hello world program and it's already like 3 megabytes of binary data. Because everything that program needs to run is built into that binary file. So you generally end up with larger binaries than you would in C, C++, but it means that you don't have to worry about your environment anymore. You no longer have to make sure that you've installed all the appropriate libraries that are, configured and set up, compiled properly for that particular operating system and all that jazz. It's just all built into Rust, and it also means that when the compiler is doing its optimizations, it's generally optimizing all the way through all the libraries you use, rather than assuming, oh, there's some black box that I have to call into and there's nothing I can do about that. So you generally end up with faster applications too. It also means that there's no dependency discovery at startup time, which helps with cold start times and stuff. Um, yeah. The only fundamental dependency that you generally require is standard lib. Um, so this is like the Rust standard lib, which then depends on the operating system standard lib, like glibc. If you don't know what I'm talking about, it doesn't matter. But basically, it does mean in general you do need an operating system in order to run Rust code. That's a fairly lightweight requirement, I think. An Alpine Linux suffices, so you can throw 10 megabyte Alpine Linux Docker image together and throw a 10 megabyte compiled Rust binary on top of that, and you're good to go. You don't need anything else. Even if you've got hundreds and hundreds of dependencies, they're all built into that Rust binary, and you're off to the races. In Python, again, I struggle to ever deploy a Python application that's less than hundreds of megabytes, if not multiple gigabytes big. And obviously, Rust compared to Python, it's ludicrously fast. No garbage collection means it's even better than like C++ and Java. You get very, very consistent memory behavior. The same inputs always consume the same amount of memory during runtime in the same pattern. And so you can actually test how much memory an operation requires deterministically. You don't have to sort of try it a bunch of times and hope that you get the garbage collector in the right conditions. So again, I normally see at least 100x speed up, and generally upwards of more like 1,000 to 10,000 times speed up, doing the exact same thing as my Python code does, but in Rust instead. Okay, so let's say I've maybe convinced you that you want to dig into this a little bit more. I have obviously not taught you much. Where would you go to learn more? I don't recommend poking around the internet and looking for a tutorial that's relevant to the kinds of things you like to do. You can do that second, but I highly recommend you don't do that first. The reason is that there's a lot of basics like the borrow checker, fighting with the borrow checker, the type system, traits. If you don't get these things right, your program won't compile and it won't run. You need to understand the mental model of how Rust code works before you can write anything that will even compile. And that is a long process. Long in terms of like hours. So I highly, highly, highly recommend, and lots of other people highly, highly, highly recommend that you start with the Rust language book. The Rust language book is one of the best maintained introductions to language I've ever come across. It walks you through some sample applications. It intentionally gets you to write very common mistakes so that you see what the compiler error messages look like and get familiar with how to converse with the compiler and not just sort of try to write code and hope for the best. It'll walk you through writing tests. It will walk you through async and regular. It'll walk you through all the basics, such that once you finish with the book, it takes, I would say, probably like 2 to 8 hours to sort of get through all the basic tutorials. Take a weekend, do it. Once you finish with the book, then you can go to all these other tutorials and follow along with what they're telling you to do, and hopefully not struggle too much with those other tutorials. If you start with those other tutorials, you will copy paste their code. It may or may not do what you asked. You will tweak one thing, the compiler will immediately start screaming at you, and you'll just give up, right? It's just hundreds and hundreds of weird, obscure, complicated error messages that make no sense at all because you haven't bothered to understand the fundamentals yet. Rust offloads complexity to compile time into the learning curve. So you have to go through the learning curve in order to use it. But once you do that, and once you understand that learning curve, you will be a better programmer in general. And you'll also be able to take advantages of all these cool features. There's also an introduction to Cargo. This is basically for like project setup, dependency management. They even include templates for doing CI/CD, whether this is building your application and creating releases on GitHub or publishing crates to crates.io. What folder layout to use for single projects versus multi-project mono repos. They've got lots of examples and built-in templates for all that stuff. It's great. So if you want to learn the syntax, go to the Rust book. I really don't recommend anything else besides doing that first. You will wrestle with the borrow checker. Everybody wrestles with the borrow checker. There is technically some valid code that the borrow checker does not allow. I can pretty much guarantee you in your first 6 months of writing Rust, you are not the exception. if you write code that the borrow checker rejects, it's because you're wrong, not it. The rules are really good, and they've done a really great job of trying to allow a wide variety of valid things. And in general, if your borrow checker says that you've done something wrong, it's because you've gotten sloppy from other languages that let you do stupid stuff, and Rust is not letting you get away with it. So it takes a lot of effort to correct your mental models, throw away things that you thought were okay but actually aren't. And as you conform to those expectations and those assumptions, you will become a better coder, even at high-level languages like Python, because you'll be better able to think through, hey, what I just did is something Rust wouldn't let me do. Why not? Oh, because it might cause this behavior. I wonder if I could, oh yeah, look, I can cause that bug right here, right? Maybe I shouldn't do that. Maybe I should make sure to copy my list before I pass into this function, because when I use that down here, I expect it to have the same values. And I want to make sure they don't mutate that object out from under me. You will be a better programmer for learning Rust. Test as you go. Tests are trivial to add alongside your code, and the test runner is built in. You can do this either via unit tests, which is sort of creating this module at the bottom of each code file and defining a bunch of tests in there. You can also do it with doc tests. This is really common in like C++ and Python domains. This is super awesome for like very simple examples of how to run your code. I wouldn't recommend like writing really robust tests in your docs because it makes really verbose docs. But for simple use cases and for examples of how to use your code, this is a really nice function to have. Also notice the triple slash. The triple slash is a special kind of comment that says, "Hey, I'm actually documenting something." So there are double slash and slash star comments for single line and block comments, just like in C. But there's also this triple slash comment, and the compiler will actually check, "Hey, use the triple slash comment, but I'm not quite sure what you're documenting." So this is actually a language feature that says, "Hey, I'm documenting something specific. These comments go with this other language object. Make sure they stay together." I don't think it throws compiler errors at you, but it does throw warnings at you that doesn't know what you're trying to document if you use that wrong. Some real world advantages. We've talked about parallelism. Multi-threading is awesome. Async is awesome. Rust cares a lot about async and has done a very good job of implementing it. If async is all you care about, go learn Go, because Go is obviously sort of the king of async. Rust implements async at a language feature, but not actually, or at a language level, but not actually the runtime. The runtime that provides functionality, async functionality, is left to third-party libraries. Tokio is a great library; everybody uses it. If you're doing like robotics or something and you want to use async, there are other libraries that might work better, but in general, everybody just uses Tokio. Iterators are awesome. Rayon makes them parallel by just trivially. There are other crates that add other functionalities to built-in data structures. I've very rarely needed anything beyond what's built in. They've got hash sets, they've got dictionaries, they've got vectors, they've got all sorts of other stuff. You can write there's great backend web frameworks. So Rust is really high performance. We've talked about very small Docker images with very short cold start times and very high performance. If that sounds like a web backend just waiting to happen to you, so does everybody else. Web backends are a really popular use case for Rust. The fact that it has good support for async just makes it even better. There's really good web frameworks. There's like 4 or 5 of them that are all competing for dominance at the moment. They're all phenomenal. Support for OpenAPI schemas and middleware and authentication, all that jazz. It's all there. Web backend is awesome in Rust. Web frontend. Wait, you can do web frontend? Yes, you can do web frontend. Rust can compile to WebAssembly, which then runs in the browser and hooks in via like one language of JavaScript that's usually built for you, and can manage your DOM. So let's go build web frontends. This is direct competitors with React, Angular, Next.js, that kind of stuff. There are dedicated web frontend frameworks like Vue that are all sort of about building nice and responsive UIs. There's this awesome framework called Leptos. I showed some docs from Leptos earlier. Leptos is super cool because it's a combined front-end back-end framework. So you write a single code base that is both your front-end and your back-end code. And it implements its own internal network communication protocols, such that you can say, hey, this front-end thing running in the browser in WebAssembly wants to call this other function that accesses the database. Well, that's a server-side function. Leptos will internally handle the networking and protocols for calling that function for you. You just call the function as if it was another Rust function. That happens over the network, runs that code on the back end, and passes the return value back over the network to your front end code, and you can slap it in the UI somewhere. Super cool framework. It's also really awesome for building UIs in general. You can build this basically on top of Electron, and then have both the front end that's doing all the DOM and UI related work, and then the back end is doing like file system, GPU access, stuff like that. So these are really cool frameworks. You can do this. It's actually relatively performant. It's not quite like React speed, but it is darn close for something that's this young. So this is super usable. I wouldn't say like go build a company off of a Rust-based front end, but there are companies that are using Rust in their front ends today, and it's working. I already talked about Leptos a bit. Super awesome. Recommend reading up more. I know there are other combined front-end back-end frameworks, especially in the JavaScript and TypeScript world. Yeah, Rust is faster and better. You can do CLIs, textual UIs. You can do game engines. There's GPU-based libraries. Lots of stuff because again, this is competing with C, C++. Low-level performance is where Rust shines. It's even trying to break into the deep learning and data science worlds. So there's this library called Polars that was trying to take over Pandas. I think its takeover is not quite succeeded because Pandas did a good job in stepping up its game. But Polars has been a pretty really sort of charged onto the scene very overnight and has remained on scene pretty well. It's a Rust-based library for doing data frame operations. What's cool is because it's written in Rust, you can use it from Rust or from Python or from other languages. Any language that can hook into it, basically any language that can hook into C can hook into Rust, and therefore can take advantage of Polars. So it becomes sort of one of the first cross-platform, cross-language data frame libraries, and is highly performed because it's written in Rust. There's also Ballista Data Fusion, which is actually both a competitor to Spark and also a runtime engine that you can plug into Spark. That's super cool, all written in Rust, high performance. Linfa is like a machine learning, scikit-learn kind of alternative. Burn is a deep learning framework that abstracts on top of libtorch or Metal or Vulkan or a variety of other GPU libraries. They even have their own custom Rust language called Rust library called kubecl that's for writing GPU kernels as Rust code. That's super awesome and is its own thing where they, I'm not going to go down that path, but they're doing some really cool stuff to not just become sort of the next big thing and the fastest, but to really make it in such a way that nobody could possibly get faster because they can just take advantage of everybody else's moves. ML on Rust stuff. Are we learning yet.com? Yes. Are we learning yet.com is great. Got to drop now. Yes, I will share the slides and the recording on Notion. It's come before. Rust is really intimately in a very intimate relationship with the Python ecosystem. This takes a few different forms. There's obviously libraries like Polars that are Rust libraries that are designed for use from Python. Even Pydantic, actually. Pydantic, in their recent version 2.0, rewrote all the core components in Rust. Rust is awesome. It basically replaces every formatter and linter that Python has ever had and runs 1,000 times faster. So things that used to be like, okay, do this before you commit, now becomes do this before you save. That's the sort of qualitative change that the speed up allows. UV has completely obliterated the Python environment space. So you used to have like conda or venv or pyenv or poetry or pipenv or one of 10 other options for managing things. UV is better than all of them and basically came up overnight. And is just ludicrously fast. Like, how can installing pip packages get faster? It can, because they basically rebuilt pip in order to make UV fast. So as sort of a Python, as Python libraries, as Python tooling, as Python management and execution, there's a Rust Python package where they're re-implementing Python in Rust instead of in C. That's a very early project, but it's going on. There's Pyo3 where Rust can actually, Pyo3 is sort of the main functionality where that allows Rust to expose a Python API, but it also allows Rust to hook into the Python dev headers, which means it can actually execute Python code from within Rust, which is fun and cool. So there's all of that. Basically, you will frequently see Python and Rust very close to each other. The two communities really love each other and are interacting in really cool ways to take advantages of the best of both worlds back and forth. So my practical experience, I've used Rust for, I don't know, 5-ish years off and on for a variety of professional work, usually as smaller tools that plug into a larger Python ecosystem. So let's talk about what I've actually encountered along that way. Compile time sucks. Everybody says this. If you look up what people's biggest complaint with Rust is, it's always the compiler is slow. I've got this library that we're working on for the cyber team right now, the SPL transpiler. The job of it is to parse out code from Splunk's query language and convert it into PySpark code. Under the hood is basically just parse from text to a syntax tree and then convert the syntax tree back to text. Actual runtime, 300 microseconds. You pass in some code and you get code out in under a millisecond on a regular basis, consistently, safely. Compile time, about a minute. So every time I make a change, it's 30 to 60 seconds of compilation to test that change. It sucks. It really does. They've been working at it for years and years and years and years and years, but the reality is there is no free lunch. If you want to keep all the runtime advantages, which are considered non-optional in Rust, you give up compile time. And if that's for sort of the dev and test versions with very minimal optimizations, you build a fully optimized release version, that can easily double the compile times. Again, freakishly fast, but freakishly fast to run, very, very slow to compile. And basically all of that's in the borrow checker, type system, all that jazz, right? It's the stuff that Rust adds, not sort of the bytecode stuff. LLVM's plenty fast and it's used under the hood. So I'll say this, but I'll say long term, I think it still saves time. And that's because as you move on with the project and get further along, not only is it preventing you from making stupid mistakes at compile time rather than at test time, so the amount of code execution you have to do in order to encounter an error and recognize that and fix it is 0, because the compiler is catching up for you, not your runtime, which means you don't even need to write the test, which means you're saving dev time because you're not writing tests and you're not running them. Even when you're talking about logical things that do require you running code in order to test something works, that code is so freakishly fast that it can be highly complicated and still run in a few microseconds, right? So you can write very complicated tests and still run them very quickly. And if you're writing tests that have to exercise large parts of your code, those large parts of your code are highly performant and they run very quickly. So as the project matures, the kinds of things that you have to test and the complexity involved in doing so runs 100 to 1,000 times faster, and that directly gets involved in your dev loop. So so I think it does make you faster and more productive in the long run, and it does make up for it. But you're going to feel it because you're constantly going to be waiting on the compiler. Python and other scripting languages are the absolute king of runtime errors. You can paste arbitrary gibberish into a Python file and hit run, and it will try. and you'll get runtime errors rather than compile time errors, right? Rather than syntax errors. Rust is the absolute opposite and the king of compile time errors. So pros and cons, right? But it does mean that you raise so many issues in the compiler at compile time that when you actually get to executing the code, there's very little else that you can have done wrong that will have compiled properly and that will try to start executing. And that means that this experience of like I wrote my code and it did what I wanted the first time. In Python, it's like 1 out of 1,000 times. In Rust, it's like 4 out of 5 times. Like on a regular basis, the code does what I want the first time. It does what I expect the first time. Because if it didn't, it wouldn't compile. Another cool thing, Rust in Jupyter Notebooks. If you've ever used Jupyter Notebooks before for frequently for Python code, like, hey, that's a nice way to tinker with stuff. You can run Rust there. How can you run Rust there? I don't know. It's complicated, but you can. This definitely takes the cake for the worst named project of all time, EVCXR. You would definitely type that into a Google query to discover how to run Rust in a Jupyter Notebook. Yeah, don't ask me where that comes from. Terrible name. So there's probably some magic going on under the hood about how they handle a compiler for you. But the reality is you can write Rust code. And in fact, for creating these slides, a lot of my code examples, especially when I was trying to create like error messages and stuff, I would run them in the EVCXR in Jupyter and get the error messages from there. So it works. It's cool. It does mean that every single time you run a cell, you are dealing with compile time. It slows down pretty quick. Very high runtime performance, very slow compile time performance, and every time you run a cell, you're compiling code. So yeah, but it's cool that you can, and for very simple concepts, it's actually very nifty that you can do that. Web as a backend, even compared to Golang, is remarkably good, and this is based not just off of I love writing Rust, and I think the frameworks are great, but watching benchmarks and people doing comparisons of Rust web servers versus Go web servers. Rust is highly performant, even in the face of languages that were designed to do that kind of thing, like Go. So it's great. I love it. It's even better with serverless because of the small Docker image sizes, because of the very short cold start times. You can throw this in AWS Lambda, build a Docker-based Lambda that runs your Rust Docker image, and from cold start from 0 instances, get latency of like 30 milliseconds. You don't get that in any other language. Not even like JavaScript with their pre-built, like pre-optimized, accelerated startups. It just doesn't happen. It is bloody fast. It is bloody good at serverless. It is incredibly efficient, not just at runtime, but actually getting to runtime too. So often use Python to sort of build out a concept of an API, get my API to the point where it's like it's the shape I want, and then translate to Rust incrementally over time. But honestly, Rust is good enough that if I have a fairly clear idea of what I want, I'll just start with Rust, and it's not that hard to iterate on. Rust as a web front end. Look, if you want to write a front end, go write React or Flutter. Rust is not the language you should be using for front ends today. But the fact that it's close, if you don't want to maintain a multi-language code base, you can write a web front end in Rust. And that means you can write desktop applications and web applications and mobile applications where the UI is in Rust. You can, and it works, and it's fine. If you've got dedicated front end people, they're not going to be Rust developers. That's fine. But if you're a solo person trying to build a UI for your thing, you can, and you're not giving up a whole lot to do so. So, I think it's inspiring. I think it's amazingly okay for how young all of this effort is. Like WebAssembly is still a beta experiment. And the fact that you can run Rust on this experimental WebAssembly and get something that's very decent. I think there's a real possibility that Rust will be a contender for front-end languages in 10 years. I've already talked about this a bunch. I'd say my practical experience is I have run Rust-based, Docker-based Lambda functions with a quarter of a CPU and 128 megs of RAM. And it's way more than enough to get 30 millisecond cold start times and sub-millisecond API response times. Additionally, because you can cross-compile to ARM, you can take advantage of cheaper processors on the cloud. So you not only, your Docker images in ECR are very small, your cold start times are very small, so your compute time is very small, so you're using very, very low compute to respond to stuff, and you're using the cheapest possible compute to do so. It's just a really beautiful stack of all the advantages to come together to make this, in my opinion, kind of the ideal language to deploy with. Building practical tools like CLIs or some data processing or some file system, like if I want to go rename 1,000 files on disk, look, I'm going to go write Python first. Let's be honest. It's enough hassle to write Rust code that if I'm doing a 30-second task or a half-hour task, I'm going to get that task done faster with Python than I would with Rust. But pretty much anything that I expect to live for more than a day, probably have to be faster using Rust than Python. I think that that used to be a lot longer of a time of a threshold. It's coming down, and I think Rust is getting really good, and I'm seeing more and more of the kinds of issues I run into Python. Like, yes, I can run the code today, but it doesn't work until tomorrow. It works the 1,000th time I try to run it. Rust works the first time I try to run it after I get past all the compiler stuff. Um, compile to every CPU, so x86, ARM, RISC-V. You can basically any CPU that you're ever going to encounter is a valid target for Rust at this point. Standard lib versus no standard lib. This means you can either run on an operating system or not. That means you can use it for robotics. WebAssembly, you can run it in the browser, or WebAssembly-based containers, which is a thing these days. I don't know if that's going to take off. We'll see. C-based API, so integrating this with C and C++ applications or anything else, basically. There's just nothing you can't do with Rust. And the real clincher, nobody wants to maintain someone else's Rust code. Yeah, I love Rust. Everybody I know who's learned Rust has loved it. And just sort of statistically speaking, people who learn Rust and write Rust love Rust. People very rarely get onto Rust and say, well, that sucked, and go find something better. But the reality is the learning curve is so intimidating that if you say, hey, I've got this Rust code base, you want to come help me? People are like, no thanks. So it's a very, very well-loved language. But if you are planning to build something on your own and then leave it to someone else, no one's going to be happy that you wrote it in Rust. Just, I don't know how else to say it. The community is substantial. It's continuing to grow. Rust is becoming more and more a part of the Linux ecosystem. There are other OSs. They're becoming part of browsers, which frankly, let's be honest, browsers are just operating systems too. High performance developer tooling, we're seeing that with Rough and UV, and other like people rewriting terminals, rewriting IDEs in Rust. Basically, we're rebuilding the world in a safe way, and generally we're finding it's more performant when we do so. The zero cost abstractions mean that we focus on the logic rather than the implementation, and we gain real advantages as a result. So people are rewriting like SSL, and like web servers like Nginx and UI frameworks like Electron. These are getting rewritten in Rust. And it's not just sort of I want it in my favorite language thing. Generally, not only are we eliminating entire classes of vulnerabilities by doing so, but generally we're finding that the code is quickly as faster. Saw a benchmark the other day for like zlib. Zlib is a basic compression. I think it's the compression library for gzip basically. And within like a year or two of development, the Rust version is faster for basically all use cases of zlib. This is just a very common thing that's kind of blowing all the old C and C++ tooling out of the water. And I think it's going to continue making inroads because you gain all those advantages, and the only thing you lose is old disadvantages, um, and tech debt. It's just constantly better. So yeah, Rust is awesome. Yeah, I'd love you to write it, but it's not the right choice for every problem. It's not the right choice for sometimes for technical reasons, sometimes for performance, for developer experience reasons, sometimes for maintainability reasons. I'm not saying it's always the right choice, um, but I think it's frequently the right choice. And if you are unscared of it, and if you kind of know, if I wanted to get started, this is how I would do it, and I might have to take a day or two to relearn things, but I could be up and running within a week or two. If that's your mentality, then it opens up a huge world of possibilities to you. Hey, my Python's code running slow. Should I, you know, figure out how to multi-process it and distribute it across a cluster of machines, or should I just rewrite this code in Rust and it'll just be 1,000 times faster and I don't need to distribute the execution anymore? I think it gets us thinking in terms of vertical scalability again, which has gotten a really bad rap in the last couple decades as we've moved to the cloud and horizontally scale everything. Um, a lot of the vast majority of problems do not require horizontal scaling. And if you can speed up your code by 1,000 times, that by itself, if not with some sane vertical scaling, will frequently get you where you need to go, without extra complexity and without extra cost. So I think having these tools at your disposal and being able to think in terms of how I would even approach a problem like that, with as few compromises as possible, I think Rust is really, really valuable in that domain. Um, my short version, I script with Python, but I engineer with Rust. If I'm doing a simple one-off task, I use Python. But basically, the moment CPU or even network or disk become my bottleneck, anytime I wish I could use more of my compute power, or anytime I wish things would just be a little faster, or I want to build a bigger system, and duck typing is getting in my way, I reach for Rust very quickly these days, and I don't regret it. I find my productivity, especially on big complex projects, to be higher in long run with Rust. That is, I get more done with less time when I use Rust, because it prevents me from making stupid mistakes and from breaking old code. Because when I've got my code working, the product, the actual artifact of my effort is faster, requires less compute power, um, and is more deployable at more scale. Right? I don't have to spend a bunch of Terraform code working around the fact that my Python has a long cold start time. I rewrite it in Rust. I don't have cold start time now. I don't have to worry about the infrastructure anymore. So my infrastructure becomes simpler. My deployments become simpler. My CI/CD becomes simpler. My environment management becomes simpler. My getting other developers up and running on Mac systems with M2s and M3s, that becomes simpler, right? Everything just gets simpler in the long run when I use Rust instead. My options are far less limited. I can do more. I can do it faster. And it makes me a better developer because it encourages good development practices like test-driven development up front rather than as an afterthought. Um, so I think I'm a better programmer, not just when I use Rust, but because I use Rust, even when I'm writing other languages. There's so much more to Rust, obviously, right? Again, this was just I want to get you unscared of it. I want to get you interested in it. This was not a introduction really to the language that is Rust. There's things with dynamic dispatch, runtime generics. We talked about build.rs very, very briefly using Rust to customize the build process. Pattern matching and match statements, we talked about that very, very briefly. They're awesome, and they're every time I go to another language, I miss having them around. Destructuring arguments and destructuring variable assignments, even refutable variable assignments. If you don't know what that means, Google it real quick. Refutable variable assignments is a cool concept. A lot of syntax features, even the ability to write unsafe code. I've never done it personally, and I hope never to have to. But the fact that you can means you're not limited, right? It's purely the best solution for each individual job. Generics are awesome. Traits are awesome. They go way deeper than what we've talked about here. Function pointers, functions as data, as values, futures, tasks, threading, channels, the type and trait system built up around those. Smart pointers, reference counting, sharing data across threads and across owners. atomics, locks, mutexes, heat management, all that is there and all that's beautiful. The built-in data structures are incredible and have a ton of functionality built in. It goes on and on. Rust is a phenomenal language with a phenomenal standard library and a phenomenal community around it. Um, its newness has meant that it has learned a lot of lessons from other languages, and basically everything that you love from Java and Python and C and C++ and everything else has at least been considered, and if relevant, has been integrated into Rust. So there's just so much beauty, and I love it. That's it. That's all there is.